Hello everyone and welcome to a new discussion which we are going to have on slope and aspects. So slope part we have already covered. This is part 3 and which is one of the again important derivatives of digital elevation model, that is aspect. As you know that when we have been discussing about triangulated irregular network or TIN, at that time we have discussed also about that aspect and slope map both are created simultaneously when you create a TIN. But in case of grid or raster or a typical digital elevation model, that has to be derived or created. So how it is done using a grid we will discuss. Before that we have also discussed about these directions, because the generally slopes are created for 8 directions. And so both are Cartesian direction and ordinal directions, both are included. So you are having north direction, you are having south direction, then you are having east, west, and then you are having ordinal direction northeast, southeast, southwest and northwest. So 8 directions. So that is why basically aspect identifies the downslope direction of the maximum rate of change in value from each cell to its neighbors. Like in case of a slope map, what it is done, it searches the 8 surrounding neighbors of a center cell, and whichever is having the lower value or lowest value, that becomes the slope basically. Now what should be the direction of slope? That can only be decided based on these 8 directions. So and this slope or aspect calculation is done with reference to the north. So always you would see that some, like in a hilly terrain, some slopes are facing north, some might be facing south and so on. So this is basically the direction of the sloping surface. That is what is aspect is. So here this example you have also seen earlier, that this is our input image and this is the output raster. Now here you would find that there are all 8 directions including one for flat, the top one, because that flat is indicating that there is no slope in the surrounding. All 8 pixels or cells are having same value as compared to the center pixel, and therefore that area is identified as flat. So in the legend you will see that there are more than 8, that is total number of 9 boxes or 9 directions are shown, but remember one direction is always about the flat. Initially when these softwares were under development, and this problem was became a sort of a big problem, because these were not able to identify very easily the flat part. But now there should not be any problem. Now you can either denote using your directions northeast or north or southeast, or you can also have in degrees. So it starts, north is always 0 and then it moves up to 360 degree and goes back to 0 again. Now when we think about the sloping surface for calculation of aspect, you have to think in sort of in 3D concept. So the all three axes are shown here. This is the x axis, this is the y axis which you are seeing here, and this is the z axis. So this angle between this plane normal vector and this, that is your theta, theta is the slope. Now with reference to the north, which is shown here, with reference to the north, the angle with that to this green line, that is that in sloping surface with reference to north, that becomes our aspect, that phi angle, and north you have already seen. So this is our xy plane on which we project, and this is very important because slope is measured in vertical plane, whereas aspect is measured on horizontal plane. and that is why this xy plane is very much required here. So, with reference to north, the whatever the direction that is projected on the flat plane, and then value is decided, whichever the direction out of 8 direction or maybe flat also. So, it can be thought as a direction of slope. Slope you get in the degrees or in percentage, that is the value, but here the direction for the aspect. So, the values of each cell in a raster indicate the compass direction with reference to north, and which is facing the slope location, and this the measured clockwise in the degrees from 0, as I already indicated here, due north to 360 degree, again to north, and completing a full circle. So, in that way we can cover the entire 360 degree or full circle. Now, flat areas, this is very important. The flat areas having no down slope in the surrounding directions are given value -1 to identify very clearly, because all these values would be varying between 0 to 360 degree, but here they may not for the flat terrain, and particularly in the software it is assigned -1 value. So, automatically it can be identified that this is a flat terrain. Here you are seeing only 8 directions in the legend plus 1 flat, but in the system for each sloping surface you can have the variations between 0 to 360 degree. Now, aspect is the basically the compass or magnetic compass direction, that is the slope faces, and a example for example, a slope on the northern edge of the Mussoorie towards the Indo-Gangetic plains is described as having a southerly aspect, and so slope when it is facing southward on the ridge. So, roughly the ridge is like east west, and if I am looking towards the south, then this sloping surface is southward, or also we say sun facing slope, because in the morning the sun is here, and in the evening the sun goes somewhere here. So, entire day the south facing slope faces sun, whereas north facing slope on the other side, on this northern side, it will have hardly any sun except in the noon time. So, that is why it is very important to find out the aspects in many studies. For example, if somebody is working for snow melt runoff modeling, then one would like to know what is the slope direction, that is the aspect. So, that it will know that whether that slope is facing the sun or not. If it is sun facing slope or southern facing southerly slope, then it will have maximum sun, maximum melting will occur. So, it depends the orientation of a glacier or a slope. Similarly, lot of human activities are most of the time in Himalayan terrain are associated only with the southern facing slopes. Even if you go to Mussoorie, the maximum number of habitation or hotels or everything is in the southern side, whereas on northern side generally you would have forest. This also becomes important in case of landslide studies, or in case of even estimating the surface runoff, because like arrangement of this in case of Mussoorie, the monsoon generally comes from south and goes towards the north. So, when it hits the southern slope, it rains there, and many times people have observed then on northern side of Mussoorie you may not have rain, whereas on southern side you would be having rain. Lot of landslides which are generally induced by an earthquake event have been observed occurring on the southern facing slopes, because these slopes are most vulnerable from landslide point of view also. So, knowing the aspect of a slope of a hilly terrain like Himalaya is very important. Now, as you know that conceptually the aspect calculation fits a plane to the z value of 3 by 3 cell neighborhood around processing or the center cell. Almost the same way as in case of slope. There also a 3 by 3 moving or roving window which goes through the entire data set and will try to find out the direction of the sloping surface or sloping cell. So, the direction of the plane faces is becomes the aspect for the processing cell. For example, here we are having a input raster. For simplicity, values have been kept either 1, 2 or 3 cell values. Here this is the output raster, and now based on the whatever the surrounding for each cell, like if I take this example of this 3, then this will be considered, and whichever is having lower value, and that may be assigned that direction. So, here see with reference to this and this all are having lower value than this. That means that for this cell this will have a slope like this, which is or aspect which is having a very high value or quite in the northwest direction, as you can also see here that it is in the northwest direction. One important point you would also note, this I have been also discussing, that one thick cell border will always be created whenever you are using this 3 by 3 kernel. So, this 3 by 3 kernel cannot move on the edges, because if it is this cell is considered, then I need further like this, which is not possible to get that data. So, therefore, this is not possible. So, that is why on the edges it cannot perform calculation, and hence no data value is assigned. So, you get, but generally you are not this is just a schematic, you are not handling such a small matrix or a small raster, you handle a raster which is quite big. So, visually you do not see that on all sides, that is the border of one cell thick is having no data, but it should have, if the program has been properly made or coded, and then it should have a border of one cell thick all around. Now, like when we have been discussing the slope, similarly here also in case of aspect, this the moving window 3 by 3 kernel visits each cell in the input raster, and for each cell in the center of the window an aspect value is calculated using algorithm that incorporates the values of the cell's 8 neighbors. So, all 8 neighbors are searched and then value is assigned. Now, the cells are identified here for our simplicity as A to I, with E representing the center cell here, for which the aspect has to be calculated. Now, taking the rate of change in both x and y direction for the cell, that is coming the slope, and for each cell the aspect is calculated using like this. So, here also you are having a constant and A10, and that is dz by dy, and then minus dz by dx. The aspect value is then converted to compass direction values between 0 to 360 degrees according to the following rule, and that rule is, if aspect is less than 0, then it is of course flat. If a cell is having 90, the aspect else is greater than 90, then cell is 360 degree, then aspect plus 90, and else then cell equal to 90 minus aspect. So, this way for each input cell the calculation is done for aspect determination, except for one thick cell all around for the border area. Now, this point I have already touched little bit, but I will go for completeness, I will go through one by one. Why basically aspect? Why we want to calculate aspect? As you know that in mountainous terrain these north facing slopes are good for certain things, but south facing slopes are good for certain things. So, if somebody is looking for a ski run or sports which are related with snow or ice, then north facing slopes are very good because they will not receive much sunshine except in noon time. Contrary to this, southern facing slopes will receive more sunshine. So, if somebody is looking for solar illumination for each location in a region for solar power development, then aspect calculation would be required. Maybe for find all southerly slopes in a mountainous region to identify locations where snow is likely to be melt first because it will get the maximum sunshine. As a part of a study to identify those residential locations likely to be hit by the runoff first. So, for lot of modeling, lot of analysis and natural disasters, the aspect becomes very, very important. Slopes vulnerable due to erosion, landslides, and most of the time you would observe that southern facing slopes will face these problems of erosion, landslides or flooding because they receive the sun, they are most vulnerable slopes. Identify areas of flat land to find an area of plain of emergency. So, even in a hilly terrain, if you run a slope calculation, you can find out which are the flat areas available, which can be used for a landing of a plane or development of an airport or runway or whatever. So, it has got lot of applications. Now, when we go towards the calculations based on a software, like example we are taking here is ArcGIS, it is not necessary that you should also use. You can also use QGIS, PMAP or Intergraph software or GeoMedia or many GIS softwares. There almost the similar options should be available. So, again two methods like in case of slope, here also two methods, one is the planar method, another one is geodesic method. So, as soon as you go for this tool aspect calculation, these two methods are, these options are available to us. Only you have to provide an input raster, you have to provide where the output raster would be located, and then you provide these two, either one these method. By default the planar is there. Help is always available, should be available in all good softwares. So, what these will do, as you know also that planar method is for 2D Cartesian and that another method and that is your geodesic method is for 3D Cartesian. So, let us go for 2D Cartesian discussion of planar method, that this computation is performed on a projected flat plane using a 3D Cartesian coordinate system. I have already told you that aspect is calculated on or measured on a flat plane, on a plane or a horizontal plane, not on a vertical plane. For the slope, it is measured on a vertical plane. So, anyway we need a flat surface or plane. Now, both planar and geodesic computations are performed using 3 by 3 neighborhood moving window. This is another standard which is followed by most of the softwares. Rather than going for 5 by 5 or 7 by 7 kernel, generally 3 by 3 kernel has been implemented. Now, for each neighborhood out of those 8, if the processing cell, the center cell is no data, the same condition as in case of slope calculation, the output will also have no data. So, if input is no data, output would also have data. Further, in computation also requires at least 7 cells bearing the processing cell have valid values. So, at least 7 cells must be there. If you are having less than 7 cells, means more than one no data, then calculation is not possible. If there are fewer than 7 valid cells, the calculation will not be performed, the output that processing cell will be no data. and then cell in the outermost rows and columns, which I have repeatedly mentioned, will have no data, because beyond that you do not have the input. So, this condition of a requirement of 7 cells cannot be fulfilled for border cells, and therefore, border cells one thick cell will have, both in rows and columns, will have no data. And this is also along the boundary, as input data said, those cells do not have enough valid neighbors. So, because this is neighborhood operation, a 3 by 3 kernel moves all around, but in the corners or in the border area it cannot be done, because you do not get the required number of neighbors, and therefore calculation cannot be done. This condition is true both in case of slope calculations as well as in aspect relation. Now, when we go for this planar aspect algorithm, and then this planar method is traditional method for calculating aspect, but there are some other development have also done. Then the moving 3 by 3 window visits each cell in the input raster, and then each cell of the center window, and aspect value is calculated using an algorithm that incorporates the values of each 8 neighbors or cells neighbors. Like here, again you are having cells in our moving or roving window, that is A to I. So, the cells are identified as letter A to I, with E representing the cell for the aspect is being calculated. Here the weight concept may not be possible, because here for all 8 directions we have to calculate the value. Now, further when we go towards the more algorithm, this is how the rate of change in x direction of a cell E calculated with the following algorithm, and whereas weight 1 and weight 2 are the horizontal weighted counts for valid cells, and for instance like this you can have different things, but this is not really implemented in that sense, that for each direction you have to have the calculations for directions. Further, for rate of change in y direction, earlier it was in x direction, similar things you would do, and then taking the rate of change in both directions x and y, for each cell the aspect is calculated using the following formula, which is the aspect equal to this constant A tan 2 dz upon dy minus dz upon dx. Now, the aspect value is then converted to compass direction, which between 0 to 360 degree according to the following rule, which we have already discussed, that the condition is here that if aspect is less than 0, the cell 90 degree minus aspect will be done. If aspect is more than 90 degree, then cell 360 degree minus aspect plus 90, and else then cell 90 minus aspect, by which you can do the calculation. Example is given here. This is my aspect calculation. So, this is my input raster, only a 3 by 3 example is given here. Values are substituted in for S direction equation, and values are substituted for the Y direction calculation, and then you get these values. After this you have to combine one, and once that you combine, the value becomes 92.64 for the center cell E, indicates that the aspect in the easterly direction. So, likewise the calculation is done. So, this was my input and this is my output. You can also see that here like 84 is the minimum, and therefore, it is having the the value which as per the slope direction, this is 114 value which is falling in this one, that is the southeast one. So, likewise the calculation is done. Now, when we go for geodesic method, that is 3D Cartesian, the geodesic method measures surface aspect in geocentric coordinate system, again that earth centered earth fixed coordinate system, and the computation result will not be affected how the data set is projected. because this projection part we have already discussed in theory. So, we have to be little careful while doing. However, in this particular calculations, that is no effect will take place. It will use Z units for the input raster if they are defined in the spatial reference, and the spatial reference of inputs does not define the Z units, and one has to do with Z unit parameters. In geodesic method produces a more accurate aspect than the planar method, but it will involve lot of calculations. So, this geodesic coordinate system, that is earth center, earth fixed coordinate system, the same concept is also used in case of global navigation satellite systems, where the center of the earth is taken like this. This is little exaggerated in sense that on the polar regions it is suppressed just to enhance that part in our diagram. So, this ECEF coordinate system is basically 3D right handed Cartesian coordinate system with the center of the earth as the origin, and where any location is represented by x, y and z, like here it is being done. So, a target location T in this figure expressed with the geocentric coordinates, that is target location T. Now, using this you can again calculate aspect more accurately, and the same discussion also about the geocentric or geodesic coordinate transformation we have discussed in slope discussion. So, I will move forward on this one. Now, in this transformations, because it has to be done for all 3D, because this is 3D Cartesian system. So, it has to be done for x, y and z also, and then there you will have this formulae, and this is for latitude, longitude and other details are also there for ellipsoidal height, because z is involved. So, that will also play a very important role. And now, in this geodesic calculation of aspect is the direction of basically downslope surface, and the measured is with reference to the north, of course on a plane that is parallel to the ellipsoidal surface, because it has to be only measured in a horizontal plane basically. To calculate the aspect at each location, a 3 by 3 again a neighborhood or a kernel is fitted around each processing cell using the least square method, and then the best fit for this LMS minimizes the sum of square difference, the dzi, and between the actual z value and fitted with z value. So, in this calculation, the plane is represented as z equal to ax plus by plus c, and for each cell dzi, the difference between the actual z value and the fitted z value, because here we are taking one ellipsoid. So, there will be a difference in the z value. So, that has to be also counted while doing this aspect calculation employing geodesic 3D Cartesian system. Then plane is fitted with this formula which is minimizes the variance, and after the plane is fitted, a surface normal is calculated like this. The surface normal is calculated, and at the same location an ellipsoid normal is also there. At the same location ellipsoid normal is also there, which is perpendicular to the tangent of the ellipsoid surface is also calculated. And likewise this since the tangent of the ellipsoid surface is considered reference plane. So, this plane becomes our reference plane. Again we are coming to that point where the aspect is always measured in horizontal plane. So, this is surface is perpendicular projected onto a plane, and finally the geodesic aspect is calculated, measured the angle alpha clockwise direction between north and the perpendicular projected normal, which is whatever is. So, if it is towards west, then this angle will be calculated. Now, let us see some examples here. This is my digital elevation model, or these are representing low elevation values, high elevation value. When this is subjected to aspect calculation, this is what I see. The aspect is here. Of course, the flat part is always. It depends whether that area is having flat part or not, but generally few cells will be counted or will be identified as flat part. So, aspect basically identifies downslope direction of the maximum rate of change in the value from each cell to its neighbors, which are 8 neighbors, and it can be thought as a direction of a sloping surface, and values for each cell in output raster indicate the compass direction, and measured clockwise in degree 0 to 360 degree. Flat areas having no downslope directions are given -1 value. Now, like in case of slope, there are also little variants are available. Either you imply for Horn method, which will bring some changes, or Jevers-Burgon Thorne method, which we also discuss these same methods for slope calculations. When we do the comparison, we find that there are variations, and let us see that Horn method and Jevers-Burgon method for certain identified cells. So, two such aspect maps were generated using the same digital elevation model, and for randomly few cells were identified which have been explored further to see what are the values they are carrying about the aspect. So, here in Horn method it is coming, say, for one cell 9 degree, for the same cell in this map Jevers-Burgon and Thorne method it is coming 10.1. So, some variations you can observe, like here in larger or in the west or northwest direction, here 215 it is coming, it is 211, 256, 259, 333 and 331. In slope map the variations were much more as compared to aspect maps created using two methods. So, definitely each method will have own advantages and disadvantages. Now, which one to choose? As I have like when we discussed slope part, we said that in like ArcGIS software or many softwares, this Horn method has been implemented. So, in case of aspect calculation also Horn method has been implemented. But if somebody would like to create this one, then the tools are also available, may not be within that software, you have to search the net. Very other important thing is that once you have created a slope map, you have also created a aspect map, you can combine these two maps and can create a new output which would be more useful than individual maps. And this is what it has been done, that slope and aspect map, this is very interesting. One can try whatever the software you are using, and this you have to be little different way you have to interpret this one. So, what it is saying that hue indicates direction of the aspect. So, which direction? Like if I am getting the these light green colors, then that is the north facing slope. If I am getting the blue colors, then I am talking of southeast color. If I am getting red color, that means I am talking southwest color. So this hue indicates the direction of aspect, sloping surface, and saturation indicates the steepness of slope, that is the value of the slope. So, more the color you are having, more the slope you are having, though it is shown in terms of percentage, does not matter. So, as you are going inside of this circle, the above one, you are finding that this saturation of colors is increasing. So similarly here, if I take any sloping surface here, I am getting very bright color in this part. So for green, so that means they are having high slope values and the direction is towards the north for the green, light green, fully saturated colors. If I am getting fully blue colors like here, which I am getting here, then what I am seeing that that means the slopes are facing towards southeast, and there in terms of percentage the slope is more than 40%. So a combined or joint or a composite can be created implying both these maps. Otherwise people generally interpret these maps separately or utilize these maps separately. But by this scheme for aspect and slope, so aspect is being represented with colors and the slope values are being represented with the saturation of colors, one can create some beautiful output. So this you can also try on your software. Another example using the same technique as it has been tried on an equator, on a crater, and there you see that the similar scheme is there, like a very saturated yellow color. That means the slopes are facing northwest direction. If I take this central part of my crater, here many colors are there which are very nicely depicting the sloping surfaces and their values. So here on the near the top you are having very high slope values and therefore colors are saturated. As soon as you go towards the bottom of that hillock within that crater, you see a completely different or changes in color or changes in saturation of colors, like as indicated in this legend or index circle. And this is available as a new in ArcGIS Pro in a new aspect raster tool function available. Otherwise in other softwares, if it is not directly available, no problem, you are having set of tools in your software, you can definitely try and can create similar products very easily. So with this I end this discussion. Thank you very much.